So where we left off last lecture, we had just been talking about electron pair geometry and molecular shape and how they are different. How electron pair geometry is based on how many domains there are around the atom, and molecular geometry takes into account the lone pairs and sort of removes them from the picture but keeps their effect in. So now we're going to talk about lone pairs and bond angles. Which takes up more space around an atom, a lone pair or a bonding pair? So think about, think about water versus methane. So in water, we have that bent molecular shape with the two lone pairs. And in methane, we have the tetrahedral, both the tetrahedral molecular shape and the tetrahedral electron pair geometry. All right? So, we said the bond angles, the electron pair geometry, the bond angles for 4 domains is about 109.5, right? But it turns out that lone pairs can affect that angle. And here's why it happens. If you think about the electrons in between C and H, they're shared pretty much in between those two atoms, right? So my electrons are a little bit far away from C, a little bit far away from H, somewhere in the middle here. But in water, the lone pairs are held tightly by the central atom. So the lone pairs in water are held very tightly to the oxygen. So, which means they are closer to the central atom. And if they're closer to the central atom, those electrons are closer to each other. So if those electrons are closer to each other, what do we get when electrons are close to one another? Yeah, so this increases repulsion. So the lone pairs increase repulsion between themselves and between the domains. So what the lone pairs do is the lone pairs actually squish. They squish the bonded pairs closer together because they are closer to the central atom. So bonds squished together. Now, it's not a huge amount. It doesn't go from like 109.5 to 90, right? So it can decrease lone pairs, decrease bond angles by let's just say 1 to 2 degrees. So the bond angle in water is not 109.5, it's like 108. Because those lone pairs are pushing the bonded pairs closer together. Make sense? Yeah, question. Yeah. Okay, so the question was, I said that it squishes the bonded pairs closer together, but wouldn't those repel each other too and get rid of it? The differences has to do with the distance from the O nucleus, right? Because the bonded electrons are further from the nucleus, so they experience less repulsion than the ones that are in the lone pairs closer. So that's why they have a slightly higher impact than the bonded pairs. So we're having a discussion about the copper cycle. Sorry, you're being recorded. It's okay. In the back, but they haven't really worked well. The copper cycle hasn't worked well. All right. Okay. Okay. So, all right. Lone pairs and bond angles. Now we get to polar bonds. Yay. Whoops. Should I draw a polar bear? Can anybody draw really well? No, we don't want to take the time. Eric, do you want to draw a polar bear? All right. I'm not good at. No, I was about to say I'm not good at art yet. I need to practice to get better. So, this is a bad drawing of a polar bear. Add ears? Oh, sorry, that was supposed to be the ear. This is the eye. All right, not important. If you are captioning this, person who is captioning this, you can cut all this crap out. All right. So, I shouldn't say bad polar bear. Bad drawing of a polar bear yet? I don't know how yet fits in there. Okay. So, polar bonds. So in polar bonds, electrons are shared unequally. And this is the result of atoms with bonded atoms, I should say. Bonded atoms with unequal electronegativity. So if I have a bond between really it's in most covalent bonds there's some level of polarity, unless they're the same atom. So like if I have a carbon-carbon bond, those carbon-carbon bond, the two carbon atoms are equally pulling on the electrons. But if I have a carbon-oxygen bond, the oxygen has a stronger electronegativity, so it pulls the electrons more tightly than the carbon does. So this leads to partial negative and partial positive ends of the bond. Now, how does this happen? Well, if we think of carbon and oxygen, and ignore octets and ignore everything, oxygen has a stronger electronegativity. That means, I'll use a very light orange. If I look at my electron density, where are the electrons residing? Well, if O has a stronger electronegativity, stronger Zeph, stronger pull, right? The electrons are going to spend more time closer to the O and less time closer to the C. All right, so if the electrons are closer to the O, that could mean that, yeah, that's okay. That means that the O is partially negative and the C is partially positive. The electrons are closer to the O, so it's not equal numbers of protons and electrons anymore. The O has a slight bit more negativity. The C has a slight bit less negativity, so it's partially positive. Now, there's one bond that we talked about in Chem 1, and we said was nonpolar. But here, we're going to use it as very slightly polar, and that is CH. The CH bond has a very slight amount of polarity. Why organic molecules tend to not be polar is because of the symmetry, not because of the fact that each individual bond is nonpolar. So this is very slightly negative. This is very slightly positive. In the past, we've talked about this being a nonpolar bond, but I just want you guys to be aware that this is a very slightly polar bond. Okay, bless you. Electronegativity values to know. Am I all right to, does anybody need me to wait? I had a request to finish the polar bear. What, that's not done? It looks perfect to me. It's not done yet. Okay. Now, electronegativity values to know. I'm not expecting you necessarily to remember these exact numbers, although it might be good. So it's based on the Pauling scale, with 4 being the strongest electronegativity of fluorine. So remember that fluorine is the most electronegative atom. It has the smallest distance from its nucleus to its outer electrons, and it's It's got a really high effective nuclear charge. Oxygen, 3.5. NaCl, approximately 3. Bromine is 2.8. Carbon is 2.5. H is 2.1. Now, a better way to remember this is not those numbers necessarily, but remember F is stronger than O, stronger than N, Cl. Br, I'm not as concerned about. It's better to understand that greater than, like that sort of progression. You can use your understanding of the periodic table to get a general idea of what this trend is, right? You know that the top right-hand side is the most electronegative. Highest F, lowest number of energy levels. Okay. Does anybody need me to wait? Yeah. Excellent question. So our noble gas is not rated on the electronegativity scale. We tend to not rate noble gases on the electronegativity scale, generally because like helium, neon, and argon just don't bond. Krypton and xenon do have a reasonably high electronegativity. At least krypton is like around 3, I think, or 3.5. But it's not one we need to know. Yeah. What is the most, the question is, what's the most electronegative naturally found substance, I guess we'll say. So we generally only think about it in terms of neutral atoms, in which case fluorine would be the one. You can like make things more interested in gaining electrons, but I don't think we need to worry about that at this point. Mainly worry about the neutral atoms and how they would be affected in a bond. Okay, so bond polarity. There are degrees of bond polarity. We can't just say, oh, this is a polar bond and this is a nonpolar bond. It's a spectrum. Right? It's not a binary. It's not on-off, polar, nonpolar. Spectrum of not polar, slightly polar, very polar, extremely polar. Okay, so to determine, you look at the difference in electronegativity between the bonded atoms. And that's the key. Just look at the two atoms, look at their electronegativities, go from there. If they're unequal, you have some level of polarity. The greater the difference, the greater the polarity. And for most of you, this should be a reasonably familiar idea. Maybe somewhere deep in the recesses of your 10th grade mind, which for some of you was last year, others was 2 years ago. Okay. So, guys, put the partial positive and partial negative charges on the atoms in the following bonds. Go. All right, you know you're absent today.
Yeah, yes. I have the test. It's just they went out to lunch. Said the door was locked.
Sorry. You're not the only one on the list. Natalie, do you know you're absent today? Okay, just making sure. I don't care, but I care for you guys to get like, because I can't change it, so it's good for you to change it. So if you get sick later and you're close to the end, you go to the house office. I would go to the house. Yeah. Yeah. Okay. So, all right, here we go. What's more electronegative, F or H? F. So that is partially negative. H is partially positive. What is more electronegative, C or N? N, partially negative, partially positive. Oh, do you guys know what this little music note is? It's not a music note, but it's a Greek letter. You can go through the alphabet. It won't take long. It's not alpha. It's not beta. Nope. Delta. It's lowercase delta. Lowercase delta. So this is uppercase delta. This is lowercase delta. Doesn't it kind of look a little bit like a D? A little bit. Ever so slightly. If you unwound it, right? Okay. So now if you think about it, guys, it makes sense that it's lowercase delta because delta means change, right? So here it's like a little change in positivity, a little change in negativity. All right. So BRBR. Which one's more electronegative? No. Neither. Neither. So Na. Those electrons are being pulled. So I like what you're thinking with that because they're both pretty electronegative, but they're not. They're equally electronegative. So like think of it as like a tug of war. Is that what it's called? Rope tug, whatever that pull thing is. Tug of war. So like if in this case, if you were doing a tug of war with yourself, it could go on forever, right? But here, like here, I did not give you the electronegativity value for S. How do you know which one is more electronegative, Nathan? They're in the same group on the periodic table. Yeah. Lesser shielding. Lesser shielding in O. Same Zeph, same effective nuclear charge, but S has more shielding, so O is going to be more electronegative. So in this tug of war, going back to the tug of war analogy, O would be pulling the electrons closer. It couldn't rip it all away, right? But it can pull them closer. All right. You need to be able to do this, and it seems like you guys are pretty good at it. All right, the inductive effect. This is something I don't think you've seen before. So if an atom is bonded to a a more electronegative atom, it can be induced to have its own greater electronegativity. Now this is confusing. So yeah, I have to see it to negativity. I have to be able to look at it to show you what it really means, I think. This definition kind of stinks. But let's look at this system right here, all right? So we'll just put H. I'm not going to do the 3D shape, even though I probably should. So we look at the CC bond, and what do we think? Is it polar or nonpolar? We would think it would be nonpolar. Turns out it is polar. It is very slightly polar. So here's why. Here is why. Okay. Now, if we look at the C and Cl, the electrons are going to want to be closer to the Cl, right? This is partially negative, but which makes the C partially positive. Now, when that C becomes partially positive, it actually acts like it has a greater electronegativity, right? Because it's partially positive, it's going to pull electrons more tightly. So what it actually does is it induces very slight partial positive on neighboring atom. So when we normally think that this CC bond is nonpolar because the Cl is pulling electrons away from the C on the right. What you're actually going to get is a very small partially positive charge on the C on the left. Yeah. Okay, so the question was, if the C on the left is slightly partially positive and the C on the right is largely partially positive, doesn't this have to equal out to have the C on the right partially negative? So it doesn't quite work that way. Think of it as like a zero-sum game, right? The sum is going to be equal to the same no matter what. It's just now this becomes slightly less partially positive, right? So it's like very negative and decreasingly positive as you go across. Whereas like if we just had the CCl bond, it'd be like negative, positive. Some of that positivity gets drained to the left, right? So it's not just like one or the other. That's a great question. Yeah, Owen. Mm-hmm. Yeah. Mm-hmm. Yep. So right. So the question, and it's a great one, and we'll talk more about this later, like much later in the year, like February, March. But if you had this molecule, and I haven't drawn it in 3D structure, would the F's pull so hard on the electrons that the bonded pair between H and C could be like totally taken by the C? So we'll talk. Well, yeah. So you could get CF3 minus and H plus. So we'll talk about, this is actually an acid. So we'll talk about acids much later in the year. There's a reason why that doesn't quite work out, but you're onto something very, very much that if you hold on to it, chapters 17, 18, and 19 will be much easier for you. All right. Okay. So molecular polarity. If we want to look at the overall polarity of a molecule, we have a method for doing that. You want to indicate the polarity of all individual bonds. Then you just look for a positive end and a negative end. All you're looking for is a lack of symmetry, or asymmetry. That's what you're looking for. If the charges around the outside are all the same, the molecule is not polar. So what this is saying is, and I need to get rid of this light blue because it's hard to see. A molecule can have polar bonds and still be nonpolar. If it's symmetrical all the way around, has the same charges all around the outside, and it's symmetric, it has symmetry, then it's nonpolar. And then large molecules, I think we talked about this last class, large molecules can have polar regions and nonpolar regions, with lipids, fats being the most common that we talk about. Although it's also true of things like DNA and most large molecules, proteins. Okay, so polarity can be measured in units called debye's. We do not need to understand the debye's. All you need to basically understand is what we call the dipole moment, which is the overall polarity of the molecule. So if it's 0, a molecule is nonpolar, and as the dipole moment increases, the molecules become more polar. So we look at something like carbon dioxide. Partially negative, partially positive. Is this symmetric? Does this have symmetry? Yes. So the way I think of symmetry, can you draw an arrow from one end, from plus to minus, that cuts through the whole molecule? There's no way I can go from plus to minus here throughout the whole molecule. Right? Even top to bottom, it's like plus here and minus here. I can't do that. 0 debye's, totally nonpolar. All right. Here, very polar, right? F, very electronegative. H, not very electronegative. So it's 1.9 dBs. The difference between 4 and 2.1, right? So here, I look at my arrow. Can I draw an arrow from plus to minus that goes through this whole molecule? I can. And this is the way we draw the arrows for polarity. You put a plus on the plus side, makes sense, and you draw towards the negative. Then you can get even crazier levels of polarity, like DMSO, dimethyl sulfoxide. 3.9 dBs, very much more polar than hydrofluoric acid. So we can already see plus, minus, boom. Don't even need the partials there. It's already told to us where the pluses and the minuses are. Those are fully charged objects. Okay, so now we practice. We have 8 minutes. I want you guys at your tables to do the 4 Lewis structures you see below and determine if the molecules are polar or not. So you don't need the dBs. I just want, is the molecule polar or non-polar? Those are also positive. Those are also positive. All right. As I'm going around and looking, I'm going to stop you guys because you guys are generally doing well, but you're missing a key idea. So for NH3, boom. NH3, we start with our Lewis dot. Boom, 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 boom. You forgot one thing. Most people did this and they saw the partial negative, partial positive, and they were done. Shape matters. So you have to draw the 3D shape to understand if a molecule is polar or not. So I would draw it like this. Then I would draw my partial charges. All right. The 3D shape matters a ton. So is this molecule polar or non-polar? Polar. All right. All right, I want to do the next. CCl4. Do the Lewis structure. So many dots. Right, so you start with the Lewis structure, and the Lewis structure allows you to see your 3D shape. So I have 4 domains around C. That gives me my tetrahedral shape. Now, each of these bonds is polar. Boop. But can I draw an arrow through that molecule that goes from plus to minus and only plus to minus? No. So we say it has no dipole. That's that arrow I was drawing. It's called the dipole. No dipole equals nonpolar. So this is an example of a molecule with polar bonds that is itself nonpolar. Yeah. Mm-hmm. Great question. So there's 2 things at play with electronegativity. There's the effective nuclear charge and the energy levels, right? The Zeph and the energy levels. How do you know which is more important? You don't. Okay. So like with Cl, that's why I gave you that list, that line. Cl is more electronegative than C. So that's where you would know that from. Yeah. Right. So O and Cl would be another example. That's why there's some that you should just sort of know, like O and Cl and N and C. Like I gave you that sort of chart, right? That you should generally know the pattern of that chart. But otherwise, like things like phosphorus and bromine or phosphorus and selenium, I would have to give you those numbers. Or you'd have to make an educated guess, and I would build that into the grading, right? See what your thought process was. Yeah, Eric. Higher effective nuclear charge, pulling tighter on the electrons. More protons. Yep. Yep. Okay. Now, here's one where the 3D drawing is particularly important. Because to me, this looks awfully symmetrical. This looks off like it has a lot of symmetry, right? But if I draw this in 3D, I can see that and you could ask me about the carbon in the middle. It doesn't matter what the partial positive and partial negative is. And then I can draw the dipole from plus to minus. So this becomes polar. Yeah, Kenny. So the question is, can you draw alternating CLH, CLH? Yeah, it doesn't matter that I drew the H's down the bottom left and the CL's on the right. Because if you turn it around, you'll always be able to get you'll always be able to sort of get this to be plus to minus. Yeah, Eli. Okay. It's okay. Scratching your head's okay. Thinking is more than okay. All right, try SO3. Why don't they what? If what? That would be easier. Right. It doesn't do it though. O does not like each other. O's do not like each other. When you watch the lecture that comes before this one, you'll see. It'll make sense. Okay. Okay. So, here's what your Lewis structure should look like. Now, here you have resonance. So because you have resonance, all three of them are equal. All three of your resonance structures are equal. So even though you have partial negativity here, essentially what you're going to get if you do the 3D is this. 3 domains, trigonal planar, partially negative all the way around, partially positive in the middle, nonpolar because it's symmetric. And it's symmetric because of resonance. So the question was, what happened to the double bond? When I draw the 3D picture, I don't draw it in. And also, it doesn't exist as a double bond because it's resonance, so it's like each one is like 1 1/3. That part is delocalized, so it can go to N. It's sort of like involved in all 3 bonds. All right, guys, I kept you a minute and a half late. I apologize. I kept you from your week.